same thing as saying 40 hundredths. Now it's time for study break number 2. If there was anything that was covered so far that you would like to cover again, now would be a good time to rewind back to the pink sheet. Moving on, number note card 8 and 9, we had graphing linear functions and slope. A function is linear if its slope is constant. To calculate the slope, if given 2 points, we plug it into the equation m equals y2 minus y1 over x2 minus x1. The slope-intercept form is y equals mx plus b, where m is the slope and b stands for the y-intercept. The standard form of a line is ax plus by equals c. This one is good for finding the x-intercept and the y-intercept. We also covered point-slope form, which is y minus y1 equals m times x minus x1. So if we were given just a point and a slope, we can calculate the slope-intercept form. Okay, the last few pieces of information you need to remember about this. Vertical lines are x equals a constant. They have an undefined slope. Horizontal lines are y equals a constant, and they have a slope of 0. The slope of parallel lines are the same, and the slope of perpendicular lines are opposite reciprocals. On note card 10, we covered linear inequalities. So if you're given y is less than or equal to mx plus b, you're going to have a solid line, and the shading is going to be below. If you have y is greater than or equal to mx plus b, you're going to have a solid line and the shading will be above. If you have y is less than mx plus b, you'll have a dotted line shaded below. And if you have y is greater than mx plus b, you'll have a dotted line and the shading will be above. The pictures below show a line with a positive slope in green and a line with a negative slope in red. They're labeled which areas would be considered above and which areas would be considered below. If we have a vertical line, if we had x is less than or equal to 2, we would have a solid line and it would be shaded on the left-hand side. If we had x is less than 2, we would have a dotted line that's vertical through x equaling 2, and it would be shaded on the left-hand side. If we have x is greater than 2, we would have a dotted line, a vertical line going through 2, shaded on the right-hand side. And if we had x is greater than or equal to 2, we'd have a solid line through x equals 2, and it would be shaded on the right-hand side. Note card number 11, we covered solving compound inequalities. A compound inequality is more than one inequality connected with the word or the word and. A disjunction uses or. We may also see a capital U, which stands for union. It means that either item can be true. For a conjunction, we use the word and, an upside down U, which means intersection, and both parts have to be true. On note card number 12, we covered absolute value equations and inequalities. Absolute value is the distance from 0 on the number line. For all real numbers x and all positive real numbers a, the absolute value of x equaling a means that x equals negative a or x equals positive a. If we have the absolute value of x is less than a, that means that x is greater than negative a and x is less than a. The conjunction can also be written as negative a is less than x, which is less than a. On a line graph, this is going to be between. Our third example, we have the absolute value of x is greater than a, which means x is less than negative a or x is greater than a positive a. An easy way to remember the difference: if we have less than, add a d to the end of the word. So we have less than is and. If we have greater, if we spell it great or, that reminds us that we use or. There are 3 simple steps to solving an absolute value equation or inequality. The 3 steps are isolate, rewrite, and solve. First, we isolate the absolute value expression if needed. Next, we rewrite as a compound statement. At this point, we are now allowed to drop the absolute value lines. Our last step is to solve. Now remember, with absolute value equations and inequalities, you can end up with no solution, 1 solution, or 2 solutions. Now it's time for study break number 3. If there's anything that you need to review that was covered in this last section, you may now want to rewind to the yellow page. Moving on, note card number 13, we covered in class. We covered graphing systems of linear equations. I'm going to cover these next few note cards in their entirety because this is the most recent information that we've covered prior to the test. The 3 types of linear systems. The first, we have exactly 1 solution. It involves 2 intersecting lines with different slopes. The type would be consistent and independent. The second type of linear system has no solution. It involves 2 parallel lines. The slopes are equal, but the y-intercepts are different. This type would be considered inconsistent. The third type of linear system has infinitely many solutions. All the points on the line are possible solutions. It includes 1 line, it's the same slope, and the same y-intercept. This type is consistent and dependent. Let's do a few examples. Example number 1, we have 2x minus y equals 3 and x plus y equals 6. We're going to be solving these systems of linear equations by graphing. First, we're going to convert this into the slope-intercept form. 2x minus y equals 3 becomes y equals 2x minus 3. This tells us that the slope is 2 and the y-intercept is negative 3. X plus y equals 6 is converted to y equals negative x plus 6. This gives us a slope of negative 1 and a y-intercept of 6. The type would be consistent and independent. If we graphed these, we would find that the lines intersect at 3, 3. When x is 3 and y is 3, the lines cross. So that would be our solution. We can check to make sure that the solution is correct by plugging the numbers back into the original system of equations. And we find that they do check out. Example number 2, we have 7x plus y equals 13 and 28x plus 4y equals negative 12. When we convert the first equation, 7x plus y equals 13, we get y